Okay, this is our title. I cannot turn to Vera, but I turn to Marcin. Do you recognize the building?
Actually, no.
Okay. This is your birthplace, Wrocław.
Oh.
This is the Wrocław Airport, the new Wrocław Airport.
Oh.
And the second picture is to Vera, who is not with us. You may see Porto, and this is related to the terrible case of vaccination. Of course, we need vaccination, not this is terrible that we need vaccination, but there is this global problem with COVID. It is impossible to solve at one place. It is impossible to solve in Europe because maybe there is a different variant in India or South America and so on. So the global problem, and it is necessary to fight this challenge. And please see there is a station, a COVID vaccination station in front of the Wrocław airport, and also a drive-through vaccination center in Porto. So may I go further? And I'm speaking about this because I need the guy who introduced vaccination from the Latin word vacca, because viruses of co was used. Do you know who is that person? No?
Jensen?
Challenging question. Handwritten notes of tartaric acid and polyhedral model. Who is that person? Louis Pasteur. Louis Pasteur, who suggested vaccination, but his early work was exactly enantiomorphism, which means opposite form, but you may know a little bit better the term suggested on the basis of Greek, of course, Peter, on the basis of Greek, chirality, handedness. Of course, this is the title of our joint show together with Marcin. Marcin, I believe, because you are the right hand and I'm the left hand, okay?
I think you are the right hand because
no, you are always right.
Letter.
You are always right. So you know,
I will accept to be L because in literature there is L and D. D is Dennis, so I will get no. Level means left.
Marcin,
okay.
For the first time, I disagree with you. You are always right. I am not always right. And you know, right is always positive. And I would like to go back a little bit to Peter Reve's lecture, because I studied this question that right is always right, the good thing. And it came out that it is maybe 99% of the languages is true, but that is, Peter, a Finno-Ugric language in Siberia where the left is good and the right is bad. So it is a very strange situation. Okay, so let's start the real lecture, because this was just an introduction why Marcin suggested this title. And again, the credit should go Marcin, because I was able immediately link via Pasteur's terminology, dissymmetric molecules. Dissymmetric molecules because you may have left-handed and right-handed molecules if some possible symmetries are missing. So there are no left-handed and right-handed cube. There is just cube. So the object should be not really asymmetric, but some object of symmetry should be missing. And if you see the two hands, left hand and right hand, you can move the left hand to the right hand overlapping position, not on the plane, but you need a three-dimensional motion. And Möbius, Marcin, you referred to Möbius in our personal discussion, came out that if we would like to move the left hand to the right hand, we need a four-dimensional space to perform this. Okay, so two societies came together, and very briefly, I would like to mention the fact that we started those type of conferences where science and arts are coming together from '89, and since that time we have triennial congresses, and would you be so kind to see, Peter, that we had 2 events in Crete already? Do you see? Yanis Vandoulakis hosted the 2013 Congress, and also 2018 was another mid-Congress meeting, and we missed you in that time. So please come next time. But anyway.
I see, that's very good.
So, and please see that the next one will be hosted in Porto by Vera. I hope that her cat is safe and she will be back, and maybe in the discussion she will speak about the forthcoming Porto Congress. And I'm very happy that Joseph is here, and of course Marcin is here, because at the opening of this summit, Joseph spoke about the need of synthesis. And basically this is our idea, that distant disciplines should be moved together and to have informal discussion. Therefore, our congresses are always 6 or 7 day events, because we don't know each other immediately. And last but not least, we have mostly plenary lectures, because there is no sense to have a session on symmetry in mathematics, symmetry in architecture, symmetry in computer science. But this is important, that the people come together and to work exactly that one which Joseph suggested at the very beginning of this summit, that there is a need for synthesis. Let's see the 3 concepts which we are dealing with. I will speak about symmetry in a very long part of this lecture, but the original meaning is common measure, and I'm sorry, no relationship with mirror symmetry at all. Please see, metron means measure, so this is common measure. Structures, Latin structura, fitting together, building. Information, informatio. Believe or not, but maybe it is not too much surprise. It means in ancient Latin, sketch, to make a drawing, and later conceptual education. Later I will discuss why it is, but if you put the question, is there anyone who used all of these 3 Latin or Greek Latin expression, my answer is Vitruvius de Architectura Libri Decem, that is 10 books on architecture. Symmetria in Latin is used 93 times. Structure in many cases, and informatio in a few cases. I gave here one example. 4.6 means book 4, chapter 6, where he speaks about sketching of the gate of temples. Okay. So let's start. Now, I'm very happy that Yanis is here, because I'm going to speak with the thesis advisor of Yanis, Bashmakova. So the main point is that this is my theory, that the concept, the Greek concept of symmetria, is related to the birth of mathematics. May I explain it very briefly why? Basically, there are 3 or rather 4 theories on the birth of mathematics as an abstract deductive science. Mathematicians definitely know the name of van der Waerden, a leading algebraist who also dealt with a Dutch person who wrote a fascinating book, Science Awakening. And he believed that mathematics with an abstract deductive system was started with in the Western world. I'm not speaking about India and not speaking about China, because that is a different story. I'm speaking about Western mathematics. It was started when the Greeks started to sort out the exact rules from the existing huge set of information which came from Egypt and Babylonia and so on. The trouble with this theory, that if you see Euclid and early Greek mathematics, they dealt endlessly with trivial statements too. For example, to prove that the sum of the angles of triangles is 180 degrees. So this is almost obvious, but they dealt endlessly with such type of questions and to prove it. So therefore, it is a little bit strange idea, because van der Waerden didn't explain why. Now, Kolmogorov, a mathematician, know his name. He was really the leading Russian mathematician, suggested that this is a general social factor, and it is really related to the Greek polis. I like this idea. Bashmakova, a historian of mathematics, and again, the thesis advisor of Yannis Vondoulakis, she believed originally, she agreed with Kolmogorov originally, but later stated that this is a unique phenomenon, exceptional case. And last but not least, I turn to Arpad Szabo, who wrote a fascinating book in the 1960s, Anfänge der griechischen Mathematik. If you don't speak German, don't worry. It was very quickly translated into English, the beginnings of Greek mathematics. If you don't speak in English and German, don't worry. It was translated very quickly into French. Marcin, if your colleagues have any trouble to read, of course, don't worry. Arpad Szabo was translated into Japanese very quickly, and so on and so on. Even new Greek translation is available. And he believed that this was, mathematics was started in the Eleatic philosophy. Eleata is currently in southern Italy, don't worry, Velaya, here is a picture about that territory. And if it is unclear, this name Eleatic philosophy, basically this is the time when Parmenides and Zeno were active. And basically the key is the proof by reductio ad absurdum. And I would like to unify all of this one. My view is very close to that one, which mentioned by Arpad Szabo, but I would like to use many components which Kolmogorov and Bashmakova emphasize, and I'm not very far from van der Waarden. Okay, let's see the history of Greek mathematics. We know absolutely nothing about directly from the Pythagorean, but later Gaudentius, Iamblichus, and so on explained. It is well known that they dealt with the monochord, with the string instrument, and so on, and which is very important that they studied the harmony, the musical speeches, and came out that if we divide the chord according to integer numbers, we have beautiful harmonies. This theory worked very well, and please see musicology. Even today, we have such expression that octave, quart, terce, and so on. We still use mathematical expression. This is perhaps going back to the Pythagorean time. This is 6th, 5th century BC. Then it worked very well also in sculptures and aesthetics. Of course, there was a debate that the head should be 1/7 or 1/8 of the height of person. So please see this idea that we may explain everything using integer numbers. It is crucial in this period. It worked very well in music, it worked very well in aesthetics. And then I turn to Marcin's opening lecture, because Marcin emphasized the problem when real numbers and irrational numbers appeared. So let's see the basic problem, but what about the diagonal of a square? Or what about a diagonal of a regular pentagon? Of course, let's try. Of course, I use modern notation because we know that the diagonal, I go back a little bit, that I'm dealing with the square and not the pentagram, because all of the ancient references explain irrationality with the square. But I know that the Pythagorean symbol was the regular pentagram, so could be that they also dealt with that one, but no documents survive from that period. Okay, so using modern notation, √2, of course, it is 3/2. I square both sides, multiply, almost, but not good. 8 is not equal to 9. Okay, it is 7/5. No, almost, but not. 141/100. Again, please square both sides, multiply. I could not make it. No, this is a possibility for a debate. I tried and I failed. You tried and failed. Maybe a genius will come and will solve this problem, but I hope that we are good enough. But let's have a debate. Let's have a debate. And if you spend some time in Greece, if you spend some time in Crete, the people are sitting in the cafe house chatting and so on. They are going to the agora and discussing, and they have a debate. But there is no sense. This is a social factor that we should argue, we should discuss. Of course, Of course, I hope that we are good enough, and if we could not make it, maybe this is impossible. But how to prove that this is impossible? And in this case, there is a proof. There is a proof. Of course, it is very important that we have no discussion. If we come together and say, I agree, I agree, I agree, we should appoint a person who will represent the opposite case, okay? And that person represent the opposite case, and I'm sorry that I tantalize you with basic mathematics, maybe late primary school, early secondary school. Let's suppose that root 2 equals a over b. This is a simplified fraction, so 2 integer. Of course, simplified fraction, we may request that is a simplified fraction. You never go to the shop, to the bakery, and you would say that I need 3 over 6 kilogram bread. You would say 1 over 2 half kilogram bread, of course. And please see in a very few steps, squaring both sides, recognizing that this means a squared is even because 2 times something. Then to recognize after a very simple lemma theorem that the square of an even number is always even and the square of an odd number is always even. It is written in blue. Then you recognize that a is an even number and b is an even number. Contradiction with the original hypothesis, with the original conjecture. I'm sorry, is it clear more or less? What I explained, it is very important to understand, because we started with a simplified fraction, and after a few steps, we realized that a is an even number and b is an even number. They were not simplified fraction. This is impossible. There is no such a and b. What does it mean? That here we have abstract mathematics. Until now, when we measured something, we dealt with the length of a building, the length of an object. Here, we made operation with a non-existing A and a non-existing B. This proof is first described in the existing body of Greek scholarly literature in Aristotle Analytica Priora. I gave here the place, and also available, of course, Euclid's Elements. So basically, we need a new terminology, and this is the point. And here I challenge Hermann Weyl and many symmetrists who claimed that the concept symmetria came perhaps from art, aesthetics, sculpture. I believe not, because the terminology which was necessary for art and aesthetics was available. Logos means ratio. Analogia means proportion. It is there exists the expression harmonia, and so on. But in mathematics, a new terminology was needed. We have 2 cases. For example, 2 and 1. These are symmetron, and root 2 and 1. So the diagonal and the side of the square. These are asymmetron. Symmetron, there is a common measure. Asymmetron, there is no common measure. I gave here the references that Plato, Aristotle, and many places we can read this terminology. So it is very important that I believe that symmetria and asymmetria as common measure and no connection with mirror reflection was born in mathematics, but symmetria, explaining everything as a ratio of integer, this was the expected case. It was very useful, as we have seen in music and in sculpture and aesthetics. So this was the good proportion. And bad proportion, it was very quickly became a term in aesthetics literature. I will give references very soon. Just I would like to make a joking note. Golden section, there is no such term golden section in Greek, akros, kai, mesos, logos, extreme and mean ratio. Golden section is not symmetria mathematically because of -1 plus root 5 over 2. So it is not symmetria, no common measure. Maybe someone would say aesthetically that this is a good proportion, but there is no reference to akros, kai, mesos, logos in the body of existing Greek literature on aesthetics. So all of the expressions which are available on the golden section, basically akros, kai, mesos, logos, because golden, this is a very, very new adjective. late Middle Ages. So anyway, it is in mathematical and astronomical calculation. But there is a new term. 1 and root 2 are asymmetron mékei. Asymmetron mékei, incommensurable in length, but commensurable in square value. And Plato has this term, symmetron dynamai, symmetros dynamai, commensurable in square. Please see, it is very easy to see this picture. If you deal not with length, but the square value, of course, you see that root 2 squared is 2, but here is a visual explanation that basically with 2 square, we are able to make the big square. So again, please see, and I finish this part here, there are 2 terms, symmetros mékei, symmetros dynamai. Symmetros mékei or mékei symmetros means commensurable in length, and symmetros dynamai means commensurable in square. Okay. By the way, in Euclid, Stoicheia, about 300 BCE, symmetry and asymmetry used as commensurability. Please note that the 5 so-called Platonic solids, Euclid used the name schemata, not polyhedron schemata, are described in a very, very end of the 13th book. 14 and 15 book are of the Stoicheia with great probability are later work, but between us, this is the weakest part. The definition is not good. Basically, explain that the faces should be the same and should be regular, but what about a double tetrahedron? What about a double tetrahedron? The double tetrahedron is made by equal regular triangles. There are 6 of them. And of course, this is not a Platonic solid because there are vertices where 3 triangles and there are vertices where 4 triangles are coming together. So Euclid failed to request very clearly that the vertex figures should be the same. By the way, it is possible to give a proof that there are just 5 such polyhedra, but I emphasize a very important fact. Symmetria is not used here. Symmetria is commensurability. What about Vitruvius, the architectura? I mentioned already 93 times he used the term symmetria, and this is always ratio of integers. Please see Cesare Ripa Allegoria. I used the 3rd edition because the first 2 editions had no pictures, but the 3rd edition has already pictures. And please see that the allegory of symmetry is related to proportion and no mirror reflection, yes. But then it is possible to understand that in modern time, maybe in a Claude Perrault, I go back a little bit, Claude Perrault, who translated Vitruvius, explained that there are 2 meanings of symmetry. There is a classical one and there is a new one, which is really mirror symmetry. I'm able to explain this novelty on the basis of Plato's symmetros dynamai, because Plato's symmetros dynamai includes the fact that we are dealing not just with ratios of lengths, but also with squares and areas. And maybe we may say that mirror reflection, which was so important in Peter's lecture, which means that left, right, we have two faces, 2 equal areas, and it is possible to explain in this way. Very quickly, already in 1794, when the first edition of Legendre Elements de Géométrie was published, it is used in modern sense, and this book had 12 editions. This is not the first book where symmetry is used in modern sense as mirror symmetry, but please understand that Legendre was a leading mathematician, and 12th edition of a textbook, this is something. Perrault was a very interesting person. He was always originally a natural scientist, maybe a Prince Charles type of person who started to criticize the architect so much. And after so much criticized, he was appointed to design the Louvre colonnade, so he became an architect. So therefore, he was a scholar who was who studied very carefully Vitruvius and became an architecture. Very briefly, the history of symmetry, at least my interpretation. I believe that it was started by the Greeks in mathematics as common measure. It became very quickly an artistic term as good proportion. It survived through the modern age. It had a special importance in proportion. And now I go back to Joseph's statements at the very beginning of his summit. So we need a synthesis. And as I suggested, the synthesis is very important, that we have a common language. And please see, at least in case of symmetry, that we have a modern time, a mathematical meaning, mirror symmetry or rotational symmetry. Later in crystallography in the 19th century, symmetry groups. In physics, especially Noether, and please see the Nobel Prize of Wigner, we have invariance. In the same times, the artistic meaning as proportion, harmony, even rhythm or orderliness survived. But please see, there is a set of expressions which could be related to both mathematics or art. So if you say balance or repetition or arch time, it is related to both of them. So let's move to structure. As I mentioned at the very beginning, structure is relating to fitting together, especially in building. But what is crucial, it is used, for example, the composition of Roman mortar and cement. You know that there is a lot of studies about Roman mortar, because this is environment friendly, and the University of Utah has a geological research group headed by Mary Johnson. They study the Roman mortar, so it is very important even for our age. And there was a very interesting discussion where Joseph, Marcin, and others participated at the very beginning. And they also discussed that we have physical, ideal, and mental structures. It was Mark's suggestion. And Marcin's definition that structure means that we have invariant subset. The structural approach became especially useful in crystallography. And very quickly, I show you the history of crystallography in the 19th century, when the local structure was understood, and the climax is Hessel when listed the 32 point groups. Then Auguste Bravais in 1848, the so-called Bravais lattices, so the translational structure of crystalline material. And finally, interestingly, in 3 places, in St. Petersburg, in Russia, Schönflies in Germany, and Barlow in England, almost in the same time. Of course, the Russians say, and they are right, that Fyodorov or Fedorov was a little bit earlier. So Yevgraf Stepanovich Fyodorov, by the way, it is a funny story because he was a professor in St. Petersburg and also in Moscow. You know the distance, okay? So do you know what happened? The train stopped in front of his home. He jumped into train, lying on the floor and studying the 230 space groups en route from St. Petersburg to Moscow and returned. So he had a lot of time to study. And anyway, we have a very important picture about crystalline materials, or if you wish, solid state physics. I have an important footnote here. I use BB, this is not Brigitte Bardot, but this is the Barlow Theorem. Coxeter calls it Barlow Theorem. I'm sorry, Harold Scott MacDonald Coxeter. I find the same theorem and a very nice proof 50 years earlier in case of Bravais' 1848 book. So therefore, I renamed the Barlow Theorem. So Bravais Barlow Theorem. It is very easy to prove. Indirect proof, similar as we had in case of symmetria, reductio ad absurdum, that 5-fold symmetry, 7 and n greater than 6-fold symmetry is impossible in an ideal periodic structure. Just 1, 2, 3, 4, and 6-fold symmetry. Please see the next picture. Sorry. Here are the representation of the two-dimensional space groups, the 17 space groups. And please see just two-fold, three-fold, four-fold, and six-fold symmetries are available. Five-fold is impossible. I had a footnote at the earlier slide that remember that Dennis Shechtman invented quasi-crystal with five-fold symmetry. This is a different issue. But this theory is about mathematically ideal crystal structures, and there are no mathematically ideal crystals. The symmetry principles became very powerful in structural analysis. I mentioned already the fact that all the possible symmetry groups were listed. I like to compare it, Dmitry is with us, who will speak about Dmitry Mendeleev. This is similar to the Mendeleev periodic table, that here I have the full list, and if you don't have some of the structures, you may invent something here. It is very useful, and this is the Fedorov-Schoenflies Barlow 230 space groups, but it was possible to classify chemical isomers, elementary particles. There are many Nobel Prize winners here, like Van Hoff, Gell-Mann. And these are also very useful to use in art, in theory of art. For example, classifying ornamental pattern. Donald Crow, a pupil of Coxeter and Dorothy Washburn, classified, for example, Native American patterns. I was interested in Hungarian patterns. And of course, we have with us Carol Beer. She made a fascinating work dealing with Islamic pattern. Architectural shapes. Frank Lloyd Wright and Le Corbusier, both of them were involved in the study of repetitive pattern. By the way, they copied Owen Jones' Grammar of Ornaments, ornaments from there. There is a beautiful book about the importance of the 17 wallpaper books in architectural shapes by March and Steedman, Geometry of Environment. March is a UCLA professor, former British professor who went to the UCLA. Steedman stayed at Open University in England. Fascinating study, for example, if you design a settlement, how to use the 17 wallpaper groups to enrich it. And believe or not, Bach-Kunstler-Fugger was reconstructed on the basis of symmetry principles. But what about social science? Structural analysis reached social science, and I would like to emphasize, which is very important, that Saussure 1916 book made a big breakthrough, and from that time, structural linguistic and structural analysis became a very important tool. And I would like to show you Levi-Strauss' book in Levi Structural Anthropology in Russian. I don't know, can you see it? This is the structural Levi-Strauss in Russian. And what I would like to show you is this. This is the original part of the book.
Actually, I cannot see. I can see on the slide, so maybe are you showing to the camera?
Yeah, I show the camera. Yeah,
so maybe you have to stop sharing.
Okay, so anyway,
no, I can see it.
Okay, it's not important. It's a small point. The Russian edition is twice longer than the original French edition. Twice longer because they extended. So this is a very important book, also Piaget and so on. And the structural idea came back to mathematics, to Bourbaki school. I have no time to go into details. Let's go to the third concept, information, informatio. We discussed earlier that the original meaning is sketch or first draft, as Vitruvius, but in ancient time, I refer to Cicero, there is a statement when information, informatio, is used to explain the meaning. Please see the quotation by Cicero and also the English translation. So to exhibit, to express the idea contained in a word. So the idea that information informatio is not only a sketch, but it could be an idea, a concept. It is available here. And now I would like to go to that part which was discussed by Marcin earlier, but I just would like to phrase Marcin's statement and to make some minor addition. First of all, I am in big trouble to say the first name. He is a Swedish American. So in Swedish, he should be Nyquist, but in America, Nyquist. So it is up to you that you would like to have a Swedish or the American pronunciation of his name. So in a Bell System Technical Telephone Company's journal, Bell System Technical Journal, Nyquist 1924, then Hartley in 1928, and finally Claude Shannon in 1948. In the same time, of course, Norbert Wiener in his cybernetics shaped what we usually call information theory. I would like to emphasize one important fact, that Nyquist used telegraph speed. Hartley is the only one who used the term information in the very title. And as you may know, Shannon spoke about theory of communication. And Hartley, usually what is called Shannon or Shannon-Wiener formula, this formula in elementary form is available in Hartley's paper. Marcin discussed it earlier, so I would not like to go into details. And I fully agree with Marcin that we should start with Hartley because his paper is very nicely written and the main ideas are available. Marcin's lecture also pointed out, please help me, which page? Page 49. There is a big mistake in Shannon theory of communication. So therefore, long life Hartley. I have here Hartley's picture and not Shannon picture. I have no objection against Shannon, please don't misunderstood, but Hartley's contribution is very important. And basically, the idea how to measure information basically with yes and no question, and basically with binary digit, which Shannon explained later in more details, also giving different probabilities of the possible object. The main idea is here at Hartley. Very quickly, information theory became popular in aesthetics. And I refer here just to two names, Max Bense and Abraham Moll, who published very comprehensive monographs of aesthetics, theory of information used in aesthetics. By the way, both of them were invited by the so-called New Bauhaus Hochschule für Gestaltung in Ulm. So they gave lectures in both scholars and also for architects and designers. Hochschule für Gestaltung, this is the secondary name of the Bauhaus at Dessau, and this was founded in 1953 after World War II, and it was a very important institution where design science as a new field in design, when design science, I mean that, or their understanding was the following one, that designer should cooperate with the people in the industry and to work out the best shape of object. Okay, now the famous experiment, the Maxwell Demon. The Maxwell Demon, I think I should not go into details, but it is a well-known example that Maxwell came out with the idea that there is a demon and we have a vessel with two parts and there is a small hole or a door, and the demon is able to open, the demon is able to see the speed of the molecules of the gas, opens and closes the door, and step by step, the demon organizes that the high-speed molecules will go to the part B and the slow molecules to part A. Ladies and gentlemen, the energy problem of mankind is solved because we are able to do heating and cooling, everything. I just would like to make a footnote here. The footnote is the following one, very briefly, how Clausius introduced the concept entropy. Of course, it was analogy of energeia, energon, and he introduced entropy. And I would like to show I would like to show the corresponding sentences from Maxwell theory of heat. I was surprised because I believe that he's speaking about the daemon. Please see the text. He's speaking, there is no daemon in Maxwell text. There is no even an intelligent person, just there is a being who can see the individual molecules. And of course, he stated, this is quotation mark from Maxwell theory of heat, 1871, that it contradiction to the second law of thermodynamics. Now, a challenging question is coming. I'm asked all of the people except Marcin. So Marcin, you are excluded, okay? You are excluded. Who is that person? I think Marcin knows it, but anyway, other people, is there any person who knows who is that person? Okay, why Marcin is excluded? Why Marcin is excluded? Because he's a Polish professor. Of course, you know the name. You know the name, a co-author of Albert Einstein. By the way, he was a mountaineer, going to the Alps, visiting various places. He died very early. By the way, it was not an accident. He became sick and died. A very important person from the Lvov school or Lemberg school. He worked together with the leading personalities of that age. By the way, Max Planck and he wrote a book together. I mean that Max Planck is not his co-author because there are separate chapters for Träge über die kinetische Theorie der Materie und der Elektrizität. Please open that book of 1914 and page 89. And he explained that the trouble with the Maxwell-Demon problem, that the daemon should be considered a part of the system. And ladies and gentlemen, I'm sorry, I'm going back to a slide. Let's remember that Hartley published his paper in 1928. So let's go ahead, and now we reach Szilard. I believed that in 1928, Hartley published his famous paper, and 1 year later, Leo Szilard published basically the so-called solution of the Maxwell-Demon problem. And it came out that it is very nice, but life is very nice theory, but life is different. When I read an interview by Leo Szilard, which was recorded shortly before his death in 1963, the record, it came out that he wrote 2 papers on thermodynamics in 1921 in Christmas, and the second one in mid-1922. But that paper of 1922 became his Habilitationsschrift. This was a very old and good tradition at some universities. It is still practiced in some places, like in Poland. If you have a doctorate, it doesn't mean that you are able to teach. Did you have professors who were very great scholars, but their lecture was terrible? Of course, in order to judge that a person will be a good instructor, it is necessary to make a so-called Habilitationsschrift. It is right work to present it. This was Leo Szilard Habilitationsschrift. There is no English expression. It is called even in English Habilitationsschrift. It was written in 1922. He defended in 1925, and he was accepted at Privatdozent, so basically a professor in Berlin, the same place when Albert Einstein and some of the big wigs were working. But this paper was not published until 1929. So this is not before Hartley. Sorry, this is not 1 year after Hartley, but this was written some years before Hartley. So it is totally independent. Please see the funny thing that this paper was not too much recognized in that time, but later it was translated twice into English, twice, not only one. And basically he came out with a formula that what type of information is needed for this Maxwell Demon or this intelligent being, and he came out more or less the same formula which was used by Hartley and John von Neumann. Immediately, John von Neumann was a good friend of Leo Szilard. Both were from Hungary, and they discussed it and they linked. He immediately suggested to link these two topics. By the way, John von Neumann suggested later in the US to Shannon, because he moved to the US some years later, to use the word entropy. So this was John von Neumann idea. And basically, I would say this is a case where where this odd couple came together. If we agree that symmetry is an ordering principle, that symmetry made order, but it was necessary to use information, a knowledge based on the measurement which the daemon, the Maxwell daemon, used. So basically, this is the solving the Maxwell daemon problem. So of course, it is possible to make such a system which is useful for heating and cooling, but it is necessary to invent, it is necessary to use a lot of pieces of information. By the way, it would be a very expensive heating and cooling, so I don't suggest to use this method. Another topic, very briefly, where symmetry principles and information came together, is the spherical coding. This is a problem that how to make an arrangement of points on a surface of a ball where the minimal distance is maximal. Incidentally, this problem was discussed in biology and discrete geometry because of the pollen has similar arrangement, and Laszlo Fejestót in 1942 came out that the solution of the problem is regular polyhedra, the vertices of the regular polyhedra. For example, the solution of the problem for 4 is the vertices of a regular tetrahedron. The solution for 6 is the vertices of a regular octahedron. The solution for 12 is the vertices of a regular icosahedron. Sorry, for 8, the solution is not a cube, but a semi-regular Archimedean, the twisted cube. Okay. May I finish my lecture very soon? I would like to speak about challenges. The challenges, please see the history of the concept of symmetry and the history of the concept of information. There were different directions. Symmetry was originally related to measure. Later, symmetry, common measure. But later it became a yes-no question. An object is symmetric or not symmetric. Is there a perfect symmetry or there is no symmetry? My information, the opposite. Information, this concept was an everyday expression. Then, because of Hartley or Nyquist, Hartley, Claude Shannon, Wiener, and a lot of other people, it became important, and it was necessary to measure. I believe that we need symmetry measures. I will have a slide about that one. So we should back to the old time and unify the concept of measurement and symmetry. The second thing, which is well known, just I would like to point out that the Shannon-Wiener approach, mathematical statistical approach, was very useful for one case, but the meaning of information is totally lost in that period. So Mackay, Bar-Hillel, and Carnap, yes, Carnap, the philosopher, in some joint paper, later a less known work by the Russian semiotician Yuri Schreider, made a lot of study into this direction, but it is not yet solved. And of course, we need a new information theory. The Hartley-Shannon theory is based on bit, binary digit, and qubit need much more geometrical approach, see the Bloch sphere representation and so on. Of course, it is possible to make a very, very trivial way to measure symmetry, for example, by the order of the symmetry group. I call it dissymmetry measure using Louis Pasteur term dissymmetry, so the difference from symmetry, of course. An object which is totally symmetric, like a sphere or a circle in 2 dimensions, the dissymmetry measure is 0, because there are infinitely many symmetry axes or symmetry plane. So 1 over infinite, this is 0. But for example, the cube has 48 symmetry operation. In mathematical term, the order of the symmetry group of the cube is 48. There are 48 operation, mirroring, rotation, and so on, by which you are able to transform into itself. This is 1 over 48. So this is, for example, clear here that the sphere is more symmetric than the cube, and the cube is less symmetric than the dodecahedron. We may feel it intuitively, but it is possible to explain. I will not go into details, but I have some paper about how to measure the dissymmetry of infinite object, basically by packing density. And packing density is very useful if we are dealing with an infinite set of objects, because it is not sensitive for a crystal imperfection, a small mistake, because there is a limb sup in the definition, limit superior, so therefore there is no trouble with that one. This measure is always between 0 and 1. And I would like to thank you the attention with that statement that we need, I believe, generalized symmetry measures. We need a generalized information theory. And I hope that these 2 fields may come together and help each other. So thank you very much for the attention, and I stop sharing.